In this session, we'll go through chapter 5, which is on strategic capacity planning. As you know, we need demand forecasting or demand forecast before we can do capacity planning, because we have to get an idea about what will be the demand in the market before we can start doing planning for what equipment, how many people, human resources, all those things will be needed. Capacity is the upper limit or ceiling on the load that an operating unit can handle. So basically, load is number of units produced. So it is in terms of number of units. And operating unit could be machine. So if the load is like on a machine, we may produce 10,000 items in a day. Or it could be how many people or workers. So workers will have their own capacity ceiling. Like they may be able to work on certain things. How many things they can do on a day? Maybe they can run a particular machine in a shift. A worker may be able to do or run 2 machines a shift. So that's the capacity of the worker depending on the skill level. Operating unit also could be a plant. It could be a department, and so on. Capacity could be in terms of equipment, space, like in warehouse, how many items you can store. So that will be the capacity in terms of space, or it could be in terms of employee skills. So basic questions we ask could be what kind of capacity is needed, how much is needed, and when is it needed. So all those things go into the capacity planning. Now, capacity decisions are very, very important because it impacts the ability to meet future demands. Because if there's a shortfall and if we are not able to meet that future demand, obviously there will be less profit. But if our capacity is more than the demand, then we are spending more money to keep that capacity idle, and obviously that will have a negative impact on the profitability. So obviously capacity decisions are very, very critical, and also because they are long-term commitments. Capacity is not something you can change on a very short notice. So if you look into past, like when Xbox was released sometime in 2005, there was so much demand that initially the demand could not be met. Same thing for another gaming system by Nintendo, which became very popular, Wii. So demand was much bigger than what capacity they had. And recently iPad by Apple, the demand was more than the capacity. So in these cases, actually, when a customer went to say Best Buy, initially when it was introduced, there were so like long queues, and also it was very difficult to get them for next maybe 1, 2, 3 weeks. It affects operating costs. So obviously, the ideal situation is going to be when capacity equals demand. So that will provide the lowest operating cost. And any other, like if capacity is more or demand is more, so that will not be the best situation. Major determinant of initial costs. So initially the cost of like equipment, machinery, or similar things, or buildings, space, based on the capacity, those costs are committed. So it is a major determinant of those initial costs. We talked about it's a long-term commitment. It cannot be changed every now and then. Obviously, it will affect competitiveness, because if the demand is much more than capacity, so there is a unfulfilled demand in the market, and the competitors can take advantage of that to cut the market share. It also affects ease of management. So if the demand and capacity are close by, then it is easier to manage things. But if capacity is much lower than demand, then always the management has to be on their toes to manage that high demand. Otherwise, they lose that business. Globalization adds complexity, like number of players increase dramatically, and it impacts long range planning. Now, capacity can be measured, like there are different metrics. One is design capacity, which is the maximum output rate or service capacity on operation, process, or facility for which it is designed. Like maybe a machine, if it can produce maximum like 10,000 items a day, if it is designed only for that, then we cannot go beyond that. It's like a car may have that upper limit, like what is the maximum miles per hour speed it can reach. So that's the design capacity of that car or vehicle. So obviously, most of the time we are not operating at that high level. Obviously, we cannot cross it, but even close to that, people do not operate. We use much less than that. So effective capacity is less than that always, and it is design capacity minus some allowances such as personal time, maintenance. There could be some scrap. It may include coffee breaks or lunch breaks. There could be periodic equipment maintenance. So all those things bring down the design capacity to effective capacity. But then ultimately the reality is the actual output. So rate of output actually achieved. And obviously it cannot exceed effective capacity. So at best it can be equal to effective capacity, but that is a very, very rare situation, because sometimes there could be machine breakdowns, or there could be some other problem issues. There could be material shortages. If a particular material is not there and assembly cannot take place, so that will bring down the actual output. So to measure capacity, there are two metrics we use: efficiency and utilization. And generally they are actually in terms of percentages. So we should multiply these by 100. So actual output by effective capacity and actual output by design capacity we can calculate. One example is given on the next slide. Design capacity was 50 trucks per day, effective was 40, and actual. So you just plug in the numbers. For efficiency you get 90%. So that looks very good, like it is just missing the effective capacity by about 10%. But utilization, which compares actual versus design, is very low, about 72%. So generally people look at this more closely because that gives an idea about opportunities for improvement. To improve, one must know that what are the determinants, what are the factors that affect capacity. Facilities, like how the facilities are designed, what is the layout. So those things have a big impact. If the facility layout is not good, if there are a lot of non-value adding activities required because of the poor design of the layout, then that will have a big impact on the capacity. Product and service factors. So product, if it is difficult to manufacture, for example, if the variability is higher than the designed specifications, for example, if this is the requirement, so you have lower limit and upper limit. And if the actual is always such that the variability, you can see it's so high that all the time there are some items which are below the lower value or lower limit, and there are some items above the upper limit. So that will cause a lot of probably rework or scrap. But then already time has been wasted, time and money has been wasted in creating those useful products, which has increased the non-value adding activities. So that will impact the capacity. Process factors, if they're not optimum, like it could be temperature, pressure, things like that, depending on what type of process you're looking at, or even the speed, if they are not optimized, that can bring down the capacity. Human factors, things like skill, training, if a person is not trained to do that particular job properly, that will bring down the capacity. There could be policy factors like a company may have a policy that no subcontracting or no overtime. So related to overtime or even subcontracting, so company management may have some policy and that could limit effective capacity. Then there could be day-to-day operational factors like scheduling and things like that. Supply chain factors. So if 10 parts are needed for assembly, even if one supplier delays everything, then it can impact the capacity. And then there could be some external factors from the government, things like related to probably pollution or emission controls for a vehicle. So that also has impact on capacity. Key decisions of capacity planning include amount of capacity needed. And sometimes we look at what is called as capacity cushion, which is 100 minus the utilization. So that gap between utilization and 100%. So when there is an uncertainty about the demand, people calculate capacity cushion. So if there is a higher uncertainty about the demand, that will lead to obviously higher requirement for the cushion. Then we have timing of changes. Like when the capacity change is warranted, the timing is very important. So we will talk about the life cycle approach where introduction, growth, maturity and decline. So at different points, the capacity requirements could change. Then need to maintain balance. So we'll talk about bottlenecks in next few slides. What happens when there's no balance, like from operation to operation, if the balance is missing, that can again create problems. Extent of flexibility of facilities. Flexibility brings a lot of benefits for capacity. Like if a machine can do different things, if it is flexible and it can deal with different varieties, obviously it will have good impact on the capacity. Now there are certain steps for capacity planning. So these are like generic steps. Estimate future capacity requirements. So always it starts with that. And then see where we stand in terms of existing capacity. So obviously between these two, there will be a gap. So how to fill that gap? People identified alternatives. And then conduct financial analysis, like for each of those alternatives, what will be the financial impact? Assess key qualitative issues and then select the one which is the best one. And then implement it and monitor. Now, forecasting capacity requirement, it could be long-term and short-term. So this is like similar to what you might have seen in POM 333 QBA class. So in forecasting chapter, we talk about things like long-term relates to overall level of capacity such as facility size, trends we talk about in forecasting, and cycles. Short-term relates to variations from seasonal, random, or irregular fluctuations in demand. Now let's look at one example of calculating processing requirement, which is related to capacity. So this is about 3 products. So annual demand for product 1 is 400 and standard processing time per unit is 5 hours. So if you multiply 5 times 400, you get processing time needed will be about 2000 hours. So for the 3 products, the total comes to 5800 hours. 5800 divided by 2000 is about 2.9. So this calculation indicates that 3 machines will be needed to meet the demand based on the data available. If you look at planning service capacity, services are always tricky. In previous chapters, we have talked about different challenges services pose. Like first one is it has to be near the customer, need to be near the customer. So capacity and locations are closely tied. Inability to store the services. Like if there are some vacant seats on an aircraft, it cannot be used in future. Today, if there's demand can be created somehow to use those vacant seats, then it's fine. But we cannot say that probably we can use it maybe next week or after a month. So that cannot be done because they cannot be stored. And then degree of volatility of demand. So sometimes there is a peak demand period and then off season. So sometimes people use some tactics like in movie theaters, the movie ticket, sometimes they give discount if people are ready to go and watch at off-peak timings. One important question from time to time a management has to face while planning capacity is whether it will be in-house or it will be outsourced. So that will depend on what is the available capacity and how much gap is there between demand and available capacity. Do we have expertise in-house to meet that demand? Are there any quality considerations? Like if it is given to say outside company and quality obviously is very important, will they be able to do a good job? It will also depend on nature of demand. Is it something which is temporary? Suppose currently the demand is, let's say, 1,000 items per month, and the capacity is designed in such a way that they're able to meet this demand very smoothly. But suddenly the demand increases to, let's say, 1,500. Now the question will come for this 1,500, that extra 500, should we increase the capacity in-house, maybe by buying more machines, hiring more people, or should it go to outsourcing? So it will depend on nature of the demand. Like if this demand is going to be consistent in future and not one-off kind of situation, like the increase is only for a month and then we are back to 1,000. So we don't want to spend money buying new machinery or hiring more people just for a month. So one has to look at the nature of demand, how reliable the demand is going to be in future. What will be the cost and what are the risks? So all that has to be taken into account while considering whether we should do in-house or outsource. Now sometimes actually a company may have such a product that they don't want to disclose proprietary information. So in that case, obviously, they have to be careful. So they don't want their business secret to be disclosed to the world. Also, they have to think about loss of control, because once they subcontract or outsource, the control goes outside the company. So that has to be kept in mind. For developing capacity alternatives, design flexibility into the systems. Like if somebody opens a restaurant with a certain capacity, they should be forward looking. Maybe in future, if the demand increases, they should have bought the land in such a way that expansion is easier. Take stage of life cycle into account. So if you recall, initially that introduction phase, the demand is less, and then there's a growth phase, and then maturity, and then decline. So depending on at what stage we are, the capacity alternatives can be developed. Take big picture approach to capacity changes. Big picture means look at systems view. look at the overall company as a business, because if there are so many different operations and if you are not looking at the big picture, then the company may suffer. So it could lead to unbalanced operations, and then that could create bottlenecks. Let me define what is a bottleneck operation. So in this picture, suppose you have machine 1, 2, 3, and 4, and machine 1 can produce 10 items per hour. Same thing for 2, 3, and 4. And these go into this bottleneck operation, which can then, you may say this is an assembly, which combines those 4 items, and then it produces 30 items per hour. So incoming is 40 if you look at the total, and outgoing is 30. So bottleneck operation, an operation in a sequence of operations whose capacity is lower than that of the other operations. You have operations in sequence. So operation 1, 20 items per hour, but 2 can produce only 10 and 3 can produce 15. So this is the lowest, so it is a bottleneck operation. Now, the key thing about bottleneck operation is that the maximum output rate is limited by the bottleneck. So the maximum will be only 10 per hour. So another thing is prepare to deal with capacity chunks. So when you are developing capacity alternatives, what happens is capacity comes in chunks. Like if you look at aircrafts, suppose an aircraft has 150 seats. So if a carrier has a company has 2 aircrafts, so 150 plus 150. But if you look at the demand, so they don't come in these big steps. Demand can be more smaller and incremental step changes. So it is not going to be easy to match that kind of pattern with this pattern of capacity where the capacity increments are much bigger. Attempt to smooth out capacity requirements. For developing alternatives, that is important. Identify optimal operating level. Now, what is optimal rate of output? So on x-axis we have rate of output, and y-axis you have average cost per item. So if we have this kind of curve, the lowest point here gives you the optimum level of output, because that will give the minimum average cost per unit. Below this point, you have, if the output rate is lower than this point here, the average cost is going to be higher. And same thing on the other side. If the output rate is less than the optimal level, so lower than that point, increasing output rate results in decreasing average unit cost. Suppose we are somewhere here. So increasing the rate of output, you can see, decreases the average cost. So that is called economies of scale. This economies of scale is if the output rate is more than the optimal level. So now we are talking about the right side of that optimal point. So the increasing the output rate results in increase in average unit cost. If you talk in terms of size of the plant, so a smaller plant may have higher average cost per unit, whereas a larger plant may have much higher output rate and lower average cost per unit. To evaluate various alternatives, one of the methods used is cost volume analysis. So we'll talk about cost value analysis in more detail, which includes the break-even point, like what should be the quantity for break-even. We do not cover actually financial analysis in very much detail here. Very briefly, we talk about cash flow and present value. Decision theory and weighting line analysis. In fact, waiting line analysis is very useful, especially for service systems. So this we cover in more detail in POM 3.3 classes. Let's say we represent V as the variable cost per unit, and Q is the volume, as you can see here. So the total cost is equal to the variable cost plus fixed cost. And the total variable cost, if V is the variable cost per unit and if Q is the quantity, then it is equal to VQ. If you look at the revenues, so total revenue, you may say if R is the revenue per unit, then this TR, which is the total revenue, so TR equals Q times R. Because on every unit, if a company is making R dollars, then if you multiply that by quantity, so that will be the total revenue. Profit, as you can see here, profit P is equal to total revenue minus total cost. So from the total revenue, if you remove total cost, that is the profit a company makes. Now, to find the break-even point, BEP is your break-even point. So break-even point in terms of Q or the quantity gives us an idea what is the minimum value we should produce to not be in loss. So at least the profit will be zero. So at break-even point for BEP, your profit is exactly zero. So we can say zero equals, if we use the top formula, now total revenue is Q times R minus total cost, we said, is fixed cost plus variable cost. So you may say 0 equals QR, and if we say fixed cost is FC and variable cost we said is V times Q. So using this, if we solve for Q, we will get, if you rearrange the terms again, we get fixed cost divided by R minus V. So for break-even point, if we use this formula, we can get what should be the quantity, what should be the break-even quantity. We will work out one or two examples. Break-even point problem with step fixed cost. When you talk about more than one machines, like 2 machines, 3 machines, you will see that there is a step function. In fact, for the first machine, there is no break-even point. For the second machine, there is a break-even point, and third machine, there is a break-even point. So using only one machine obviously is not going to be profitable. Always there will be a loss because the cost is more than the revenue all the time. Let's look at 2 problems from the book first, and then we'll move on. So this is number 3. So fixed cost is given as $9,200 per month. Variable cost, or you can say we use the symbol V for that, and that is 70 cents per unit. Revenue, when each item is sold, we get 90 cents. So revenue is 90 cents. Now in part A, to find, you may say Q, and we can put BEP for break-even point. And as you had seen on the previous slide, the formula is fixed cost divided by R minus V. So once you put those values, so that gives us 46,000 units. So break-even point is 46,000 units. So anything less than that, it is not going to be profitable. Now in part B, you can use profit equals So this is the total revenue minus fixed cost plus VQ. So when you have profit, like what will be the profit when you have 61,000 units? So the profit, if you input the values and calculate, you should get about $3,000. Because 61,000 is 46,000, so obviously it is going to be profitable. And if you produce more, it is 7,000. That gives a profit of $8,200. Is $45 per customer, and the variable cost $20 per customer. To calculate break-even points with 1 and 2 machines, let's say 1 machine and then 2 machines. So what we are given with this fixed cost with 1 machine is $2,000, and with 2 machines 3,800. So this was 2,000. And the range, as per the problem, is if we produce up to 100, and with 2 machines we can go from 101 to 200. So our QBEP, using the formula FC divided by R minus V, would come to about 80 with 1 machine and 152 with 2 machines. Now in part B, the question is which one we should go for if the demand between 90 and 120 customers. So obviously we should use 1 machine because the break-even point for 1 machine is 80. So anything more than 80 will give profit. And the demand range is 90 and maximum 120, and 120 is less than 152. So if we have 2 machines, there will be losses. So that's why we should go for 1 machine. The assumptions of cost volume analysis. So only 1 product is involved. So that's the assumption. Everything produced can be sold. So we have to see, like sometimes the assumptions may not be realistic, but in this analysis, this is what we have to assume. Variable cost per unit is the same regardless of volume. Fixed costs do not change with volume. Revenue per unit constant with volume. So we are not giving any discounts with volume. Revenue per unit exceeds the variable cost per unit. So basically, it will be profitable. Now, very briefly, financial analysis, we said includes cash flow, which is the difference between cash received from sales and other sources and cash outflow for labor, material, overhead, and taxes. So while doing this analysis, all these factors are included, and it also includes what is called a present value, the sum in current value of all future cash flow of investment proposal. As mentioned earlier, we spend more time in QBA, POM 333 class. It is a helpful tool for financial comparison of alternatives. So those of you who have already completed that class, so in that class we talk about decision trees and things like that under different situations, under conditions of risk, uncertainty. So this is suited for capacity decisions. So people do this a lot. Waiting line analysis. This is very useful, especially for service. Waiting lines occur across a wide variety of service systems. All of us are familiar, and obviously in QBA POM 333, we go into much more details. Waiting lines are caused by bottlenecks in the process. So in fact, if you want to identify a bottleneck operation in any company, it's very easy. You look at different operations. Wherever we see maximum inventory, that's the bottleneck process. So waiting lines are caused by bottleneck areas because they are very slow. Waiting line analysis helps managers plan capacity level that will be cost effective by balancing the cost of having customers wait in line with cost of additional capacity.